Hi everyone, welcome to this video. I am Kai Sumalinog from 3BS CEC and this is CE 311A Structural Theory. So for today's video, we are going to talk about the Hardy-Cross method or the moment distribution method and the approximate analysis using the portal method. So let us proceed with the problem. Here is our frame. Draw the shear and moment diagram of the frame shown in the figure. Use the Hardy-Cross method or the moment distribution method and compare your answer using approximate analysis. So we have here our frame and we have a fixed support A and B and we have a lateral forces 9K and 18K. So we have here the length of 30 feet from A to B, and from F to D we have 15 feet, and D to B is 15 feet. We have constant inertia at every members given in the frame. Now let us go here. We have our FBD of the actual frame, the same fixed support at A and B. We are going to solve it using the moment diagram method. So we have here the frame subjected to MQ1 moments and the frame subjected to MQ2 moments. On MQ1 moments, we have the delta 1 in here, and on MQ2, we have the delta 2 in here. So let us proceed with finding the member stiffness of the frame. So we have here the FBD, and we're going to find the member stiffness factor. This is by the formula K is equals to I over length, or the inertia over the length. So for members K, A, C, B, D, C, E, and D, F, it will be equals to I over 15. And for K, C, E, and K, E, F, that will be 2 over 30 times I, which is equals also to I over 15, since 2 over 30 is 1/15. Now we have already the member stiffness factor. We can solve now the distribution factors of the frame. So we have here the distribution factors formula, which is dF is equal to K over the summation of K. So for dF AC and dF BD, it is equal to 0 because it is a fixed support. The distribution factors of a fixed support is 0, and the distribution factor of a roller or hinge support are the 1. So for CA, CD, and CE, its distribution factors will be equals to 1, or I over 15 over I over 15 plus 1 over 15 plus 1 over 15. These are the summation of the total member stiffness factor. Since there are 3, so there are also 3. And CA, CD, CE are all 1 over 15. So, manipulating it, that would be equal to 15 over 45. Na-cancel natin yung I, since maging 1 man siya. So, okay lang, hindi na siya isulat. So, 15 over 45 is equals to 1/3. And for CE and EF, we have here sa CE and EF, the K will be 1 over 15, and then that will be 1 over 15 plus or over 1 over 15 plus 1 over 15, that will be I over 30. So I over 30 ang denominator natin. So for numerator is I over 15, that would be equal to 1/2. So we already have our distribution factors and our member stiffness factor. Now let us proceed for the fixed end moment. We all have here the formula FEM is equal to 6 EI times the delta 1 over length squared. So for AC and CA, we will have the result of a positive result. For BD and DB is positive also, DF and FD is negative, and CE and EC is negative. That is for the delta 1. For the delta 2, we have a fixed end moment at CE and EC, and then 6 equals EI delta 2 over 15, which is the length. And assuming that the fixed end moment 6 EI delta 1 over 15 squared is equals to 100K or kips per feet. And for the delta 2, that will be 6 EI delta 2 over 15 squared is equals to 100k per feet. So we already have the member stiffness factor, the distribution factors, and the fixed end moment. Now let us go here on the table. What we did in this table is we just put all the values and we use the formulas. So we have the joints A, C, E, F, D, and B. And we have a member on each. On joint A is AC, on C is CA, CD, and CE, and E. On E is EC and EF. On F, it is FE, FD, DF. On D, it's DC and DB. And on B is BD. So we have mentioned the distribution factors of these members, which are the 0 and 1/3. Plotting out on the table, on the AC is 0, CA is 1/3, CD is 1/3, CE 1/3, and on joint E, we have a 1/2. On F is 1/2, and on D is 1/3, and on B is 0. So we already assumed the value of the fixed end moment, which is 100k per feet. Plotting it on our table, on the joints A, that will be 100. On C is 100, CA is 100, CD is 0, C is -100, and E is -100. By the way, the blank spaces on this table are equal to 0. I just didn't put it there. So that will be the fixed end moments. Okay, now let us proceed on how we are going, or we are able to get the balance of the C1. So what are we doing, or what formula we have used is we used the summation of, by the way, this is distribution factors, fixed end moments, the balance, the carryover moment, and that's it. And this one is the final moment, which is not really the final. So it is just the summation of the moments from here. So let's go. How to get the balance is we are going to get the summation of fixed end moments on that joint times the distribution factor, or multiply the distribution factor. So on joint A, we have here a member AC. So the total FEM of that is only 100. So 100 times 0, which is the distribution factor, that will be 0. So that's it. That is 0. Let's change the color into red so we can see it clearly. Again, as I have mentioned, the how to get the balance is to add all FEM on that member times the distribution factor. So 100 times 0 is 0. Now on the CA, we are going to make like this. So on CD, we have an FEM of 0. So 100 plus 0 is 100 minus 100, which is because it's negative. So it's 0 times the 1/3, that will be 0. So all of these here are 0 on the balance on the joint C. And on the joint E, we have here FEM is -100, right? Times -1/2, that would be 50. Since 100 divided by 2 is 50. So that's how we get that. Anyway, it's 0 in here. So the same process with everything on the other joints. Now let us proceed on the carryover moment and how we got it. So how do we solve the carryover moment? Is like this, diba? This is 0 in here. So we are going to, because AC and CA are 1, we are going to cross it over. So that would be 0 divided by 2 is equals to 0. And we put it on this portion. So that will be our answer. Wait a minute. Let me clear it so you can see it. So 0 divided by 2 is equals to 0. You put it here. The answer that you can get in this balance in here is the carryover on the other joint. So here, we will have the 0 divided by 2 is 0, right? Divided by 2 is 0. So that would be 0 also in here. It's crossed like that. It will cross over to the same member. So if it is not connected or not the same, that will be we are going to divide it by itself, 0 divide 2, and we put it on its lower portion, which is 0. So that is how you get that thing. So by doing it so on and so forth, that's how you will get the answer. So on the balance, what are you gonna do is you add all the moments in here present on the member AC or the joint A. That will be 0. So times 0, it's 0. It's here. And if it is on the joint C, adding all the ZOs, I mean the COs on the joint C, that will be 0 plus 25 times 1/3. That will be equals to negative 8.3. So that will be our CD. So that's how we do it. And then the same process on the carryover moment. You multiply it divided by 2, and then you put it on the crossover. It's 0. 8.3 divided by 2 is 4.2, and so on and so forth until we reach the end on the C7, the nearest. So the total final moment of the MQA will be in here. So that is the result of the summation of that moments present in that members. Now let us proceed in looking for the value of CX in a member, or I mean, and the vertical horizontal forces in each, or I mean, let us proceed on searching for the values of the forces present in each member of the frame. So let us start here in EC. So we got the moment, or nagkuha tayo ng moment from the E. So it will be counterclockwise since the sign convention of all things is positive. It's counterclockwise, upward, and to the right. Those are the sign conventions needed for the moments. So we have a force here, a horizontal force CX. We are going to put it on the formula. That will be CX times the arm length, which is 15, minus 85.3, which we got it on the CE in here on the table, which is on the CE, that is 85.3, and the 61.73 is from the EC. So here, that 2. So it is equals to 0. So CX will be 9.8K, and it is going to right, that will be positive. And CX and DX have the same length in here. They are similar. So the DF and EC are similar and parallel and have the same size, so it is just the same. So CX equals to DX will be 9.8K. CX is equals to DX will be the same. Okay, CX and DX is equals because it has the same value on the what you call this one, on the frame. They are equals. So that will be DX is also 9.8K. On the next one is this one on the member CA. So we got the moment at C. That will be AX times 15 plus 97.04 plus 94.19. So we got AC in here, the 97.4, and on the CA, which is 94.19. AX will be 12.75K. Going to the left, it is negative. So AX and BX are the same because they have the same length. They are equal. So AX equals to BX. BX will also be 12.75K. Going left, that is negative. Now let's proceed here. Since we already got the values of X, or the horizontal on that members, we are going to get the QA1, or the value of QA1 and that is adding all the horizontal forces. So on QA1, that will be plus 9.8 plus 9.8 is equal to 0. This is on the C, okay? We got it on the member EC. So that will be QA1 is equals to 19.6K. Going to the left, that is negative. For the horizontal forces, on QA2, we are going to add up all the forces on horizontal. That will be, this is on the member AC, so that is QA2 minus 19.6 minus 12.75 minus 12.75 is equals to 0. So we will get the value of QA2, which is 45.1K. Those are all summations of the moments on QA. And remember, QA. Okay, let us proceed on the MQB, or the frame subjected to MQB moments. So we have here our table. It has the same process with what we have done on the summation of moments on QA. So the same process, same things on what we have done. It is just that it has the different value for the FEM. It has different. So there is only fixed end moments at CE and EC, and then FD and DF. The rest are zeros. So the same process on the crossover, which is 0 divided by 2, and then plotting it on the crossover. So that's it. Now let us proceed on getting the moments at E. So we got the moments at E. If the summation of total moments present in that is CX times 15, which is the arm length, plus 58.81 plus 52.95, which is equals to 0. So 58.81 is from here, from the EC and the CE on this final moments. So that will be the CX is 7.45K, and also the DX is 7.45K. So those are negatives. Now finding the moment at C, so that we can get the AX and the BX. That will be the AX times the moment arm length, which is 15, minus 11.8, which we got it from the table CA here. And the 23.5, so AX will be 2.35K. So going to the right, that will be AX will be 2.35K. Going to the right, that will be positive. Now we are going to get all the horizontal forces present on the table, on the frame, on EF and CD. So we have here the values given. That will be QB1 plus 7.45 minus 7.42 is equals to 0. So QB1 will be 14.9K, and it is positive. On the horizontal forces on the lower portion of the frame, that will be QB2 plus 14.9 plus 2.35 plus 2.35 is equal to 0. So QB2 will be 19.6K. Going to the left, it is negative. So we already have the values in that. Now let us proceed on the superposition method on horizontal forces at joints. So in this portion, we are going to get on the joints C and E. So R1 is the lateral force 18K. So plus joint CE, let us get at the joint CE. So R1 is the lateral force plus the C1 QA1 minus C2 QA2 is equal to 0. This is for us to be able to get C1 and C2. So this is the lateral force 18K plus C1 times the 45.1 minus C2 19.6 equals to 0. So we already have our first equation since we can't get its value pa. So this will be considered as our equation 1. Put it in it is equation 1. Now let us proceed for the equation 2. That will be R2, which is the 9K lateral force. C2QB1, that is C1, plus C2QB2 is equal to 0. So negative 9 minus C1 times 19.6 plus C2 times the 14.9 is equals to 0. So 19.6 times C1 plus 14.9 C2. So that will be our equation 2. We already have our equation 1 and equation 2. Manipulating it all, we are going to get this formula. C2 is 45.C1 minus 18 over 19.6, and C2, equation 2, 9 plus 19.6 times C over 14.9. So manipulating it, putting it, everything in here, transposing it, we are going to get the value of C1, which is 1.5447 or 1.545. And then putting the C1 on one of these formulas, we will be able to get the C2, which is 2.6360. Getting the member end moments in M in actual frame. So that will be, we are going to solve this one. This one, we are going to get the moments present in this frame. So using the formula, M is equals to C1M QA plus C2M QB. So we have here the members AC, CA, CD, CE, EC, F, FE, FD, DF, DC, DB, and BD. Okay, we have here the final moments at MQA, the values given as we have solved on the tables in here. And then we also have on the MQB the values. So we have that. Now we are going to plot it on the formula, which are this one, and the C1 is given and the C2. So we are able to get the final moment of that members. So for AC and BD, plotting all the 1.545 times the 97.04 plus 2.36 negative times negative 11.8, it will be equal to 118.82 kips per feet. And then for CA and DB, that is 83.45 kips per feet. For CD and DC, that is 106.88 kips per feet. C and DF is 23.5. EC and FD is 44.44, and EF and FE is negative 44.45 kips per feet. So those are the member end moments M in actual frame and on each members. So here is our actual moment distribution. That is how our moments looks like on the frame. So solving for reaction, HA will be equals to MCA plus MAC minus over L, and equals to negative 83.45 plus 118 minus 0.82 over 15, that is 13.48 kips. Negative, that is negative. And on HC, that will be negative MEC plus MCE over length, which is 44.44 plus 23.5 over 15, that is 44.53 kips. And again, it's negative. So looking for the moment at, or the value of EY, we are going to look for the EY and FY. First, we are going to find or get the moment at E. The summation of moments at E will be Fy times the moment arm length, which is 30, minus 44.44, which is the moment here. That will be minus 44.44 is equal to 0. So Fy times 30 is equal to 88.88 divided by 30. Fy will be 2.96 kips. And on EY, solving for the vertical forces, the summation of vertical forces is equal to 0. So EY plus 2.96 is equal to 0. And EY is 2.96, negative. So looking downward. So that is how our EY and FY. Now on the CD, the value of CY and DY. CY and DY. So we are going to get the moment at C here. So summation of forces present in that, dy times 30 minus 106.88 minus 106.88 equals 0. So dy will be 7.13 k upward. It is positive. Okay, solving for the total or summation of vertical forces present on that member, that will be Cy plus 7.13, which is the dy is equal to 0. Cy will be 7.13k looking downwards, and it is negative. So this is our shear diagram and bending moment diagram. This is how it looks like. So we have the values here on EF, on November EF, EC, FD, AC, and then BD, also on C and D. So that is our shear diagram. And for the bending moment, we have here. So that's it. That is the shear diagram and bending moment diagram on the Hardy-Cross method and the moment distribution method. We already have the shear diagram and bending moment diagram using the Hardy-Cross method and the moment distribution method. Now let us go to let's try to solve it using the approximate analysis using the portal method. So that will be our frame, our structure. So we have here the force 9k. Disregard the value. Those two are x. So 9k is equals to the lateral force 9k. So x plus x is equals to 9 equals to 2x. So x equals 4.5. So that's how we got our values in here. And on the lower portion, we just add all the lateral forces 9k and 18k. So the result divided by 2, which are the 2 x's. So it will be 13.5k and 13.5k. Okay, so that is how we got the values in that. Now getting all the same process, 44.5 in here, the same process what we did, divided by 2, so we get the 2.25. We already have the value, and then here and 13.5k starting at this point, and we all got its values, and also the moment A on this portion and the fixed support, that will be 101.25 kips per feet, and on the moment B is 101.25 kips per feet. And on the portal method, this is how it looks like. There is no big difference between the two, the shear diagram using the Hardy-Cross method and the portal method, but on the Hardy-Cross we have all the smallest details. We can get the smallest details as we wish, and we are going to conclude, we're going to get a better results on the Hardy-Cross method, but it is very lengthy, unlike the portal method. So that's it, everyone. That is our video, that is our presentation, and that is my report on the using the Hardy-Cross method, the moment distribution method, and the portal method. Thank you for watching.